and welcome to lecture 19 of analog integrated circuit design. In the previous lecture, we were looking at a typical op amp data sheet, what specifications are listed, and this we did based on our knowledge of op amp so far as a macro model using transconductors or voltage controlled current sources. Okay. What we listed as typical specifications of an op amp, a standard op amp are given here. You have the DC gain and saturation voltages, AC magnitude response, which also gives you the phase margin for unity gain. You can also calculate the phase margin for other values of gain by appropriately lowering the magnitude plot. You also have the slew rate, which relates to the maximum rate of change, and this comes about because internal to the op amp there will be some current limitation, which limits the rate of charging of the integrating capacitor or the compensation capacitor. And you have offset and noise voltages in the circuit, which lead to some error in calculating the difference between the desired and the actual values, and consequently give you an error in the output of the feedback circuit. And we also have maximum ratings, like the maximum supply voltage the op amp can tolerate and maximum supply current the op amp can tolerate. Okay. These specifications are true even for op amps that are used in ICs for specific purposes, but in general these specifications hold good even for these specifications are necessary even for op amps used in ICs for specific purposes. They are more relevant for a catalog part op amp for which you will study the data sheet and you will use the op amp. When you design an op amp for an integrated circuit which you are designing yourself, you can change some of the parameters. Okay. Out of these things, we will look at the effect of offset right now. Later, we will see how the offset comes about, but for now, we will see what offset does to our circuit. This op amp is supposed to be something that takes the difference between two values and integrates it with a certain multiplying factor omega u, which is the unity gain frequency of the op amp. Okay. Now, in reality there will be an error that is added, which I will call VOS, and that is equivalent to adding a voltage VOS here. Okay. In other words, it is like having a voltage source in series with the input. Now, this voltage is a random quantity, its statistics are known, but its exact number is not known, that is why it is a problem. Okay. Now, what does this do to our circuit? It depends on which circuit we are talking about. In general, you can see that what is being compared by the op amp is not the voltages V1 and V2, but V1 minus V2 plus VOS. Okay. There is an error that is added to the comparison. So, consequently, when steady state is reached for constant inputs, the inputs here, the two inputs here will be at the same voltage. Okay. So, that means that the two inputs V1 and V2 will not be at the same voltage. Whatever we used to call the virtual short before, the voltage difference between the two inputs will now be separated by the offset voltage or VOS. Okay. So, this leads to errors in the circuit. Now, first of all, the DC characteristic of the op amp itself, V naught versus VE. Okay. Ideally should have been a straight line passing through the origin and having a slope of A naught. Okay. Now, clearly now you see that if VE is 0, the output will not be 0. Okay. So, what happens now is that instead of being like this, the output will be like that. Okay. So, when the input V e equals minus V o s, the inputs here will be 0 and the output will be also 0. Okay. So, this point will be equal to minus V o s, the way we have defined it, and that is the offset voltage. Okay. And in fact, the effect of the offset can be quite significant, because the slope here, this A naught is very large. Okay. It can even be up to a million. So, it can be that due to the offset voltage, when the input is 0, the output is already saturated. Okay. So, this is the offset voltage in this case, and when the input is 0, the output is already saturated, right. This is not because the offset voltage itself is very large, this is because the gain can be extremely large. Okay. This curve is drawn with a modest slope, because I have to show the characteristics, but if I plot V o and V e on the same scale, the characteristic of the op amp looks something like this. Okay. Ideal characteristics look something of this sort, it is almost vertical. You can see that a very small shift in this will take the op amp to saturation when the input is 0. Okay. So, this is an important point, because you cannot use an op amp in open loop, right. If you look at only this black curve given here, it looks like I can use the op amp as an amplifier like this, okay, without having any feedback. But because of offset, what happens is, very likely the op amp output will be saturated when the input is 0, and you do not know exactly what input you have to apply to operate in this region. You have to operate in the high slope region of the op amp, so that you get all the benefits of negative feedback. So, the only way to fix this situation is to have DC negative feedback around the op amp, so that the op amp gets biased in the high slope region. Okay. So, circuits which do not have DC negative feedback will have an op amp output that is most likely saturated. You cannot use such circuits. Okay. Now, what does this offset do to our amplifiers? Let us take our prototype amplifier. This is R, this is k minus 1 R. Okay. And the op amp has an offset V o s. Okay. So, if I apply V e, I have to find out what V o is, and for simplicity in this case I will assume that the DC gain is infinite, that is, this op amp acts like an ideal integrator with a unity gain frequency omega u. Okay. So, that means that when it reaches steady state, these two voltages, the plus and minus inputs of the op amp shown here, are identical to each other. Okay. So, what does that mean? The voltage here is V naught by k. So, the voltage here also will be V naught by k, and that will be equal to V I plus V o s. Okay. So, this means that the output of the amplifier will be k times V I plus k times V o s. Okay. So, this is the desired output, and k times V o s is the offset in the output. Okay. So, this means that when the input is 0, the output is not equal to 0, but the output will be equal to k times VOS. So, the effect of the offset is generally to create an offset in the output as well. Now, in this particular example, it turned out that the desired output is k times the input voltage, and the offset that we get is also k times the offset voltage of the op amp. The gain from the offset to the output is the same as the gain from the input to the output. Now, this does not have to be the case, depending on the circuit we build, the gain from the input to the output and from the offset to the output can be quite different. So, let us take the other amplifier that we are familiar with, which is the inverting amplifier. This is the offset voltage, and let us say I call this R and again k minus 1 R. If I apply Vi, let us see what happens to the output voltage. Now, the way I have drawn this op amp is, this is the complete op amp. Okay. So, this is the negative terminal and that is the positive terminal, and the op amp that is drawn inside is free of offset, and the offset is represented by this voltage source VOS. Okay. That is a very common representation of the offset. You represent the offset as a voltage in series with either the plus terminal or the minus terminal. What will the output voltage be? These two voltages will be equal to each other, and we know by resistive division formula that the voltage at the minus input will be Vi times k minus 1 by k plus Vo times 1 by k, and that will be equal to VOS. Okay. So, now we can write Vo to be minus k minus 1 times Vi plus k times VOS. Okay. This is the desired output minus k minus 1 times Vi, that is the gain of the inverting amplifier, and you also see that there is an offset k times VOS, and here you see that the gain from the offset to the output is k and gain from input to the output is minus k minus 1. Okay. So, in general the two do not have to be equal to each other, you have to analyze the circuit to see what the gain from the offset is and what the gain from the input is. And you can also think of it as just a circuit with two inputs, one of the inputs is the offset voltage and one of the inputs is the actual input voltage that you want to apply, and you will have different gains from the two sources. Okay. Now, later we will see that any noise voltage of the op amp will be represented by a voltage source similar to the offset in series with either the plus input or the minus input. Okay. Now, so far I have been representing the offset like this. It does not have to be only that way, I could also represent it in series with the negative input, okay, where this op amp here is considered to be offset free. Okay. These two representations are equivalent, and that is very clear when you consider the input voltage applied here VE, and you see that the voltage difference between these 2 points will be VE plus VOS, and it is exactly the same here as well. Okay. VE plus VOS. Okay. So, that is about the offset of the op amp. Now, you can see that the offset creates an error in the output, it creates an offset in the output as well, and you have to either choose an op amp which has a low enough offset for your application, or find some way of getting rid of the offset even though the op amp itself has an offset. Okay. Now, there is one more specification of the op amp which we did not consider earlier, which is known as the common mode gain, which is usually specified by the common mode rejection ratio. Okay. Now, what is this thing? Again, the op amp is supposed to consider only the difference voltage between its two inputs. Let me call it VIP and VIM, and V equals VIP minus VIM, and the output is supposed to respond to only VIP minus VIM. Okay. It should look at only the difference. Now, because of limitations of the circuits with which the op amp is built, it turns out this is not exactly true, right. So, what happens is that it also responds to the average value of VIP and VIM. Okay. For instance, if you consider the op amp at DC, the output is supposed to be A naught times VIP minus VIM, where A naught is the DC gain, which in ideal conditions is infinity. Okay. In reality, it turns out it is A naught times VIP minus VIM plus some common mode gain ACM times VIP plus VIM divided by 2. Okay. This VIP plus VIM divided by 2 is the average voltage of the input or common mode input of the op amp. Okay. And this ACM is known as the common mode gain. This A naught is called the differential gain, okay, because this VIP minus VIM is the differential input voltage. Okay. Now, this ACM should ideally be 0. So, that the op amp responds only to the difference input VIP minus VIM, but in reality it is not 0. It will be much smaller than A naught, but it will be non-zero. Okay. To figure out how small it is compared to A naught, you can specify the value of ACM itself, but usually what is done is to specify the value of the ratio A naught by ACM represented in dB, 20 log to base 10 of that one. Okay. So, let us say if A naught is I will just take some arbitrary example. Let us say the value of A naught is 1000 and the value of ACM is 0.1, then the common mode rejection ratio will be 80 dB. Okay. So, you can see that the ratio A naught by ACM to represent how large the differential gain is compared to the common mode gain. So, that is called the common mode rejection ratio and it is represented in dBs. Okay. And this is also part of the op amp data sheet. Now, what is the effect of this common mode gain? That we will see. Actually, the two classic circuits that we have, the inverting amplifier and the non-inverting amplifier, give perfect examples of what can happen because of common mode gain. Okay. As I said, ACM should ideally be 0. In reality, it is much smaller than A naught, the differential gain, but non-zero. Okay. Let us take the non-inverting amplifier. Now, I can't simply use the difference voltage here, I have to use these two to represent the output of the op amp, to calculate the output of the op amp. So, V naught is given by A naught VIP minus VIM plus ACM VIP plus VIM divided by 2. Okay. And we have the relationship due to the feedback network, which says that this VIM equals V naught by K, and we also know that VIP simply equals the input voltage Vi. Now, from this we can calculate V naught exactly using algebra, right. Please take this as an exercise and calculate V naught using these relationships. It is a bunch of linear equations, it is really simple, but I am not going to do it here, I will just explain the situation more intuitively. Okay. So, what I will do is, first of all, let me assume that the differential gain is very large. Okay. And initially I will consider a case where the common mode gain is 0, right. If the differential gain is very large, let us say reaching infinity, and the common mode gain is 0, this is the situation that we had earlier with the ideal op amp. So, what will we have? VIM will also be equal to Vi because of the virtual short. Okay. And the output will be just K times Vi. This is the ideal case. Now, what I will do is, I will assume now that the common mode gain ACM has a small non-zero value. Okay. What will that do? That will change the output. I will assume that the output is not changed significantly. Okay. So, if the output is not changed significantly, then VIM is not changed significantly. Output is changed, but not by a very large quantity. Okay. That is my assumption. So, what does it mean? VIP and VIM are more or less the same as before, and the average value VIP plus VIM by 2 will also be exactly the same as before, and it is just equal to Vi. Okay. So, in this circuit, the common mode input of the op amp equals the input voltage. Okay. That is very clear. If the input varies by some amount, the negative input follows that. So, the average value of the two is exactly same as the input. Okay. Now, because of the common mode gain, I will assume that the output has some change, output experiences some change, and that is equal to the common mode gain times the average value, which is the same as Vi. Okay. So, what happens because of this? The output voltage will be the ideal value of KVI plus the common mode gain times the common mode voltage, which happens to be Vi in this particular circuit. Okay. So, what is the problem? First of all, it looks like the gain is not exactly what we want. Okay. The gain is K plus ACM instead of just K, that is a problem in itself. The value of ACM is uncertain, so this causes a small error. But the bigger problem is that although I represented the transfer from the common mode voltage to the output as a linear function, I said that the output is simply the common mode gain times the common mode voltage. It is frequently not that, it is some nonlinear function of the common mode voltage. Okay. So, the output will be some A naught times the differential voltage plus some nonlinear function of the common mode voltage, which I have approximated to be ACM times VIP plus VIM by 2. Okay. Now, because it is nonlinear, the error that gets added here is also nonlinearly related to Vi. Okay. So, that means that the output is nonlinearly related to Vi and it creates distortion and so on. Okay. So, this can be a problem. Now, you see that in this case the common mode input to the op amp is exactly the same as the input signal that you apply, and this will contrast now with the inverting amplifier, in which case the common mode voltage turns out to be much smaller. Okay. Now, I did not go through these calculations. What I did was I just assumed that the output voltage changes by a small amount, so that the effect of that on the input common mode voltage is not very large. Okay. I calculated the common mode voltage assuming that there is no common mode gain, and then I used the same thing in later calculations. you can do the exact calculations and see how much the error will be. Okay. The error will not be very large, it is some shortcut that you can use if you understand the relative quantities of different things. Okay. Now, let me take an inverting amplifier. Like before, you can put down all the expressions including the relationship between the input voltage of the op amp and the output including the common mode gain, okay, and solve for the output. I will not do that, I will use the same shortcut I used before. I will calculate the inputs of the op amp assuming there is no common mode gain and use that common mode voltage to calculate the error due to common mode gain. Okay. It is very easy. First of all, again I will assume A naught tending to infinity, A naught being very large. Okay. What happens then? The voltage here is the same as the voltage there and that is equal to 0. Okay. So, if A naught is very large, these two voltages are close to each other. Even if A naught is finite, this voltage will be a small fraction of the output. Okay. So, you can see now that the average value of these two, the common mode voltage is very close to 0. Okay. So, the inverting amplifier has an almost 0 common mode input for the op amp. Now, because of the differential gain, the output of the op amp had to be okay. This is the ideal output. Now, we also have plus ACM times the common mode voltage which is 0, which is almost 0, even if it is not exactly 0, it is quite small compared to Vi and Vo. Okay. So, this is the error due to ACM. Okay. As before, it is not just ACM times the input common mode voltage, it is some nonlinear function of the common mode voltage, but it does not matter because the common mode voltage itself is so small that the error due to that is small. Okay. So, this brings out one of the key differences between inverting and non-inverting amplifiers. Let us say you wanted an amplifier of gain 10, you could make it either as an inverting amplifier or a non-inverting amplifier. Now, how do you choose one versus the other? You will look at different performance metrics. For instance, the non-inverting amplifier has an infinite input resistance, the inverting amplifier has an input resistance equal to R, the resistance that we use here. Okay. But there is also another significant difference based on the common mode performance of the op amp. You expect that because the common mode voltage is very large in a non-inverting amplifier, the effect of nonlinearity will come out much more strongly. We saw that the non-inverting amplifier has a very large common mode voltage. So, the any effect of common mode gain and consequent nonlinearity will be much larger in a non-inverting amplifier than in an inverting amplifier. In an inverting amplifier, the common mode voltage is 0. So, these effects will be very small. Okay. So, sometimes in very distortion sensitive applications, you will tend to use inverting topologies instead of non-inverting topologies. Okay. So, that is about the standard op amp and the op amp's data sheet and so on. So, in the rest of this lecture, we will discuss one more interesting circuit, a transimpedance amplifier which is used frequently with photodiodes. Now, this is somewhat disconnected from the rest of the lecture, but I will show this just so that you get a better understanding of loop gain and stability criteria and so on. So, we have already articulated the stability criteria in many ways. First of all, you can look at the loop gain and use the Nyquist plot to find the stability, and in most practical cases you do not have to draw the Nyquist plot, you can simply look at the Bode plot and ascertain stability. And we see that only around the unity gain frequency it has to have a 20 dB per decade slope. Okay. So, the circuit that I am going to discuss now also illustrates this in a slightly different way. Okay. As you probably know, a photodiode responds to light shining on it by producing a current. Okay. So, usually you have a reverse bias diode, and then when you have some light shining on it, there is some current that tends to flow through the diode. Okay. Normally, a reverse bias diode carries no current, but in a photodiode when light falls on it there will be a current. Now, this is represented by a current source. Okay, I will just call it IS, and the photodiode has a reverse bias capacitance which can be significantly large. I will call that CD. Okay. So, we will use this as the model for the photodiode, and this is used very frequently in communication systems where you have light coming in through an optical fiber and then it shines on a photodiode, it converts it to a current, and that current has to be converted to a voltage that is detected later. Okay. So, what do we do? There are many ways of converting a current to a voltage. Okay. We have already discussed this in different context earlier. What are the possibilities? First of all, I could simply connect a resistance across the photodiode. Okay. Now, the transfer function between this IS and this voltage is given by IS divided by 1 by R plus SCD. Okay. Or in other words, the output voltage is IS R by 1 plus SCD times R. Okay. So, at DC the transimpedance is R, and the bandwidth of this is a first order circuit. So, I am assuming you are familiar with the bandwidth of the first order system, it is 1 over CD times R. Okay. And please remember that CD is a quantity that is given to you, you cannot change that, you certainly cannot reduce it, you can add to it. Now, you can see that if you add any more capacitance to it, the bandwidth only reduces, but you cannot reduce it. Okay. So, what does this mean? For a given bandwidth, R is fixed. Okay. So, if you want bandwidth to be greater than let us say some omega BW, this means that R is smaller than 1 over CD times omega BW. Okay. Now, if you want a large bandwidth, you can only have a small gain. In this case, the gain from the input current to the output voltage is the DC transimpedance, and that is R. Okay. And if you want a wide bandwidth, you can only have a small gain, and that is a constraint. Okay. And there is nothing you can do in this circuit to increase the gain. If you increase the gain, the bandwidth will reduce. Okay. So, instead of this kind of circuit, let us try and use a current controlled voltage source and see what happens. I know what a current controlled voltage source looks like. This is a current controlled voltage source, and I connect my photodiode to this, and the capacitance that will always be there with the photodiode will get connected to that point. Okay. I will assume that the op amp has a certain unity gain frequency omega u, and I will model it as an integrator Okay. So, the transfer function of the op amp itself is omega u by s, right. So, I will assume that the DC gain is infinite, that is okay for this circuit. It turns out you have to consider the effect of the DC gain only if you are looking specifically at the accuracy of the amplifier around DC. Okay. So, if you are looking at stability and other things which we are going to look at, you can usually model it as an integrator and get away with it. So, what will be the voltage here? If this has a transfer function of omega u by s, the voltage here is nothing but minus V naught s by omega u. Okay. So, the current flowing here is V naught 1 plus s by omega u. The current flowing through the capacitor upwards is V naught s by omega u times the admittance of the capacitor, which is S C D, and the sum of these two, this and that, has to equal I s. Okay. Sorry, I made a mistake here. The current flowing through this resistor is V naught times 1 plus s by omega u divided by R, of course, and we have plus V naught s by omega u S C D. Okay. So, I will take R to this side and I will have okay. So, now the transfer function V naught by S turns out to be R, which is the DC gain or the DC transimpedance of this, divided by 1 plus s by omega u plus s square C D R by omega u. Okay. This is a second order system. We know that the standard form is okay. So, this is the damping factor. Alternatively, we can represent it as a quality factor. It will be 1 plus s by q omega n plus s square by omega n square. Okay. The damping factor and quality factor are alternative ways of representing the same second order function, whether it is critically damped, over damped or under damped. Okay. The damping factor is usually denoted by zeta and the quality factor is denoted by q. The two are related by that relationship, and an under damped system will have zeta less than 1 or quality factor greater than half. Okay. A critically damped system will have zeta equals 1 or quality factor equals half, and finally, an over damped system will have zeta greater than 1 or a quality less than half. So, you can use whichever you are comfortable with. In this case, I will use zeta. Okay. Let us calculate the quality factor and the natural frequency. The natural frequency is omega u by C D times R, okay. And we know that 2 zeta by omega n is 1 over omega u from this by comparing this to the standard form. So, zeta will be Okay. Zeta is given by half square root of 1 by omega u C D and R. Okay. So, in other words, let me repeat the results I had. V naught by I s R by 1 plus S by omega u plus S square C D R by omega u, and this transfer function has a DC gain of R, a natural frequency omega n of square root of omega u by C D R, and a damping factor zeta of half square root of omega u C D R. Okay. Now, we would like to constrain the damping factor. It may not be 1, but certainly it cannot be very small like 0.1 and so on. So, usually you use damping factors of somewhere between 1 and half. Okay. For simplicity, let us assume that zeta happens to be 1 over square root of 2. Okay. So, this means that half square root of 1 over omega u C D R is 1 over square root of 2. Okay. So, omega u C D times R happens to be half. Okay, that is what comes out of this one. Now, the natural frequency is given by square root of 1 over 2 C D R times 1 over C D R, which is basically 1 over square root of 2 C D times R. Okay. Now, it turns out that when the damping factor is 1 over square root of 2, the bandwidth of the circuit is exactly equal to the natural frequency, and that is 1 over square root of 2 C D times R. Okay. Now, what is this saying? So, first of all, please be aware of the constraints. We want to make the damping factor equals 1 over square root of 2. Okay. So, that means that the value of omega u should be adjusted to be 1 over 2 times C D times R, and the bandwidth of the circuit will also be 1 over square root of 2 times C D times R. Okay. These are the expressions that we get for the transimpedance amplifier that we have made, that is a current controlled voltage source for converting the current of a photodiode to a voltage. Okay. So, just to compare this with the previous case, originally I had a photodiode which I model as a current source with some capacitance C D. Okay. The first circuit I had was to simply connect a resistance across the photodiode to get a voltage. If this is I s C D and I have a resistance R. So, the output voltage is I s times R. The gain of the circuit is R and the bandwidth of the circuit is 1 over C D times R. Now, I have my new circuit, which I think is an improvement. Instead of having a resistor directly across the photodiode, I will use a current controlled voltage source. Okay. I s. Now, in this case also the DC gain is R. Okay. And the bandwidth, it depends on the damping factor and so on, but here what I have calculated is for a damping factor zeta of 1 over square root of 2. Now, it turns out that for this particular value of damping factor, the bandwidth of this circuit equals the natural frequency of the circuit. Okay. So, it will be 1 over square root 2 C D R. Okay. The damping factor is 1 over square root of 2, which means that the 3 dB bandwidth happens to be equal to the natural frequency of the second order system. Okay. Now, is this really an improvement? First of all, it looks like the bandwidth has reduced. By the way, to get this particular bandwidth and in particular this particular damping factor, we need to use an op amp whose unity gain frequency is 1 over 2 times C D times R. Okay. In fact, it is not a good idea to use an even higher unity gain frequency for the op amp. We will see that it will result in a smaller damping factor or a lot of ringing. Okay. So, what it means is we can use this circuit, it converts the current to voltage, but for it not to have ringing, we are, let us say we choose zeta equals 1 over square root of 2, we have to choose a particular value of omega u. Now, it is assumed here that the diode capacitance C D and the DC gain R are given. Okay. Now, the problem with the first circuit was that once these two are given, the bandwidth is fixed. Okay. So, if you are specified a large gain, you will have to suffer a low bandwidth. Now, it seems the same is going to happen even when we have the op amp. Okay. When we have the op amp, first of all we can have a high natural frequency by using a high unity gain frequency for the op amp, okay, by choosing an op amp with a very high unity gain frequency. But it turns out that that also reduces the damping factor to unacceptable levels. Okay. So, another way to look at this is to examine the loop gain. Now, for loop gain calculations, I do not need the source and I can break the loop here. I will assume that this is an integrator of the form omega u by s, and the transfer function from here to there, from this point to that point, is 1 over 1 plus s C D times R. Okay. And let me plot the two magnitudes separately. This is omega u by s, or rather let me plot this 1 by 1 plus s C D R. Magnitude response looks something like that, where this is 1 over C D times R. Okay. So, this is the Bode magnitude plot. Now, how do we choose omega u? Let us say we choose some omega u over here, okay, some very large value of omega u. What happens then? The response of the op amp, the magnitude response of the op amp will be like that, and the combined loop gain response, which is the product of these two, omega u by s times that whole thing, will be something like this, and after this point it falls off at 40 dB per decade. Okay. This is minus 20 and that is minus 40. Now, this is clearly a problem. Our stability criteria show that when loop gain crosses unity, the slope has to be around minus 20 dB per decade. That is, it should have an integrator like behavior or a first order behavior when it crosses unity gain frequency. We have analyzed this in so many ways. We said that it should behave like an integrator, or the Nyquist plot should cross the unit circle around the negative imaginary axis and so on, and this is clearly not doing that. And this is a problem because we have chosen a very high value of omega u. So, let us try a smaller value of omega u. So, let us say we had our omega u somewhere over here, okay. Then everything seems fine, because then the loop gain will be something like this. It will have a first order behavior up to some value way below the unity loop gain frequency, and it will do that. Okay. This is perfectly fine. Now, this is the value required for damping factor of 1 over square root of 2, and that corresponds to somewhere over here. Okay. In this case, what happens is the loop gain will have 20 dB per decade slope up to this point, just beyond the unity loop gain frequency, and from there it will fall off at 40 dB per decade. Okay. So, that is the limit, and this is why we can't have a very high omega u. So, even if you are able to build an op amp with a very high unity gain frequency, it is useless. Given the value of CD and R, you simply can't choose a higher value of unity gain frequency and prevent severe ringing. Okay. So, what can be done about this? There is a clean solution to this as well, which can be also thought of in many ways as usual. We know that ringing appears when we have too much delay in the feedback loop, that is one way to think about it, or when we have a low frequency parasitic pole and so on. Now, one way to counter the effect of the pole is by adding a 0. Okay. Now, from the output of the op amp to the input, we have a first order system R and CD, which has a transfer function 1 by 1 plus S CD R. Now, to this we can add a 0 by adding a capacitor across the resistor. This will have a transfer function 1 plus S CF R divided by 1 plus S CF plus CD times R. So, this can be thought of in many ways. You can think of it in the frequency domain, this 0 will provide a phase lead. Okay. Alternatively, you can think of it as the resistor takes a long time to charge the capacitor. So, you provide a lot of charge by connecting a capacitor across it. So, that if you apply a step at the input, the output also will be a step, okay, because the CF provides, the capacitor CF provides a lot of charge. Okay. Or alternatively, you can think of it as a fast path, that is bypassing the slow path R. So, either way you can I mean the result is that in the frequency domain you have a 0 that provides phase lead, or in the time domain you have an advance compared to what you had earlier, advance meaning a negative delay. Of course, the delay of the circuit is not negative, it is just less than what it was before. Okay. And again I will use an op amp with a certain unity gain frequency omega u. Okay. Now, what happens if I write down the node equations here? If this is V naught, this voltage has to be minus V naught S by omega u. So, I know that minus V naught S by omega u times SCF plus G plus SCD. G is the reciprocal of this resistance R. Okay. Minus V naught SCF plus G has to be equal to IS. Okay. Minus IS in this case. So, if I solve for this, I will get V naught by IS to be RF divided by S square CD plus CF RF by omega u plus S 1 over omega u plus CF RF plus 1. Okay. If you compare this to what we had earlier, it is exactly the same. If you reduce CF to 0, this is what we will get. Okay. Now, what is good about this? Let us again try to get a damping factor of 1 over square root of 2 and see where it leads. Remember, our problem was that regardless of what op amp we use, we are not able to get a higher bandwidth given the photodiode capacitance CD and the required DC gain or the DC transimpedance R. Okay. So, once the CD and R are given, our bandwidth seems to be fixed. Now, in this case, natural frequency omega n equals square root of omega u divided by CD plus CF times R, and 2 times the damping factor divided by omega n will be 1 over omega u plus C f times R. Okay. Now, I will choose a damping factor of 1 over square root of 2, it is a convenient value, and for this particular value of damping factor, the 3 dB bandwidth happens to be equal to omega n, but the conclusions will be the same if you do the calculations with any other reasonable value of damping factor from half to 1. Okay. For this damping factor being half, I will have square root of 2 times square root of CD plus CF R divided by omega u to be equal to 1 over omega u plus CF times R. Squaring both sides, we have that equal to 1 over omega u square plus 2 times CFR by omega u plus CFR squared. Okay. So, this part cancels with that part, and we have CFR square to be equal to 2 times CDR omega u minus 1 divided by omega u square. Okay. Now, given omega u, you can choose CF for this damping factor. It basically gives a relationship between different quantities, but what we are finally interested in is the value of omega u. Okay. Which is equal to square root of omega u divided by CD times R plus CF times R. Now, I have the equation for CF times R. I know that CF times R squared equals 2 CD times R times omega u minus 1 divided by omega u squared. Okay. So, if I substitute this in here, I will get square root of omega u divided by CD times R plus square root of this expression, which is 2 CDR omega u minus 1 divided by omega u, and which finally simplifies to omega u divided by omega u CDR plus square root of 2 CDR omega u minus 1, okay, and square root of this whole thing. The expression looks complicated. But the point I want to make here is that the 3 dB bandwidth depends on omega u. Now, both the numerator and denominator depend on omega u, but the numerator is directly proportional to omega u, whereas the denominator has it under some square roots. Okay. So, the point here is that it is possible to use a faster op amp, meaning an op amp with a higher unity gain frequency, and increase the bandwidth of this circuit. Now, what is the condition for this to happen? We need to introduce a 0 with this capacitor CF and adjust the value of CF according to the expression we just derived, okay, which is this one. CFR whole square should be 2 CDR omega u minus 1 divided by omega u squared. Okay. So, to increase the bandwidth of this particular circuit, what you need to do is choose a high bandwidth op amp and choose the appropriate value of the capacitor. Okay. So, this circuit is very commonly used with photodiode transimpedance amplifiers. The photodiode inevitably comes with some CD. So, you can have some R and this CF. Okay. Now, quickly if we look at the loop gain here, what happens is that the feedback network from here to there has a loop gain that looks like that. Okay. starts with unity at low frequencies and has a pole at 1 over Cf plus Cd times R, and it also has a 0 at 1 over Cf times R. Okay. So, the gain becomes flat again at high frequencies and the phase shift also goes away. So, now if you multiply this with, let us say, an op amp which has a unity gain frequency somewhere over here, the overall loop gain will look something like that. It will have a minus 20 dB per decade slope here and minus 40, and it comes back to minus 20. Okay. So, the slope changes twice, and when it crosses the unity loop gain frequency, the slope is minus 20 dB per decade. So, it is possible to have the circuit to be stable even with a very high value of omega u. Okay. Now, this is an interesting example where by using a 0 we introduce a phase lead or a reduced delay and make the circuit stable, and also the bonus that we get for the transimpedance amplifier is that when you are given a diode capacitance CD and a resistance R, you can still increase the bandwidth by using a faster op amp by using appropriate CF. Remember, this was not possible with either of the two circuits by connecting a resistor directly across the photodiode or by using a transimpedance amplifier. Okay. Now, just a last quick remark, this technique is also useful when we have an inverting amplifier. Okay. Now, there will always be some parasitic capacitance here. If you reduce this combination to a Norton equivalent, we will have a current source at the input, and that looks exactly the same as that one, okay, except for a shunt resistance R1. So, in this case also, by putting a capacitor across R2, you can do some things. If you run into stability problems because of this capacitance, I will call it CD, it is not due to any diode, it is just the parasitic capacitance at the input. You can introduce a 0 and fix the situation. Okay. Now, when you have resistors, you also have the freedom to simply reduce the resistor values, so that the parasitic pole moves to high frequencies. Now, when that is for some reason not permitted, you can introduce a 0. Okay. Thank you. I will see you in the next class.